When light is applied to an atom or molecule, does the atom or molecule acquire thermal kinetic energy? Yes, when light is applied to atoms or molecules, they can gain kinetic energy. Light has both wave and particle properties. As a wave, light is an electromagnetic wave, consisting of oscillating electric and magnetic fields. As a particle, light is a quantum called a photon. Photons have energy, and their energy is proportional to the wavelength of light. When light is applied to atoms or molecules, the energy of the light can excite the electrons in the atom or molecule. Electrons exist in different energy levels within an atom or molecule, depending on the atom's or molecule's principal quantum number. If the energy of the light is high enough to raise the electrons in the atom or molecule to a higher energy level, the atom or molecule becomes excited. An excited atom or molecule is unstable, so it releases energy and returns to its ground state. The energy released is in the form of light. This process is called absorption. During absorption, the energy of the light is converted to kinetic energy of the atom or molecule. Therefore, when light is applied to atoms or molecules, they can gain kinetic energy. What happens when protons or neutrons absorb light? Protons and neutrons are uncharged particles, so they do not directly absorb light. This is because they do not interact electrically with light in the same way as electrons do. However, they can interact with light within an atom. When protons or neutrons interact with an atom, they can cause nuclear reactions or other high-energy physics phenomena. These reactions are studied in nuclear physics, and they include nuclear reactors, neutron capture, and neutron scattering. These phenomena play an important role in nuclear physics and other fields of science. In summary, instead of directly absorbing light, protons and neutrons can interact with light within the nucleus, causing nuclear reactions and other nuclear physics phenomena. Specific examples. 1. When an atom or molecule absorbs light and then returns to its ground state, releasing the energy in the form of heat, the temperature of the atom or molecule increases. 1. Therefore, light can be used to heat objects. 2. An atom or molecule that absorbs light in an excited state can also react with other atoms or molecules. 2. These reactions can cause chemical reactions. 3. An atom or molecule that absorbs light in an excited state can also cause nuclear reactions. 3. These reactions are used in nuclear bombs and nuclear power plants. Therefore, when light is applied to atoms or molecules, various phenomena can occur, one of which is the increase in kinetic energy of the atoms or molecules. Can the reaction to light vary for each atom? Yes, the response of atoms to light can vary depending on the type and composition of the chemical element. The electron configuration and energy levels of an atom determine how it interacts with light. What is the difference between hydrogen, helium, and carbon? Here are some examples. 1. Hydrogen. Hydrogen is the simplest element, consisting of one electron and one proton. 1. When hydrogen atoms absorb and emit light, they produce spectral lines at specific wavelengths, energies. 1. These spectral lines are produced by transitions between the energy levels of the hydrogen atom. 2. Helium. Helium is an element with 2 electrons, and has a more complex electron configuration than hydrogen. 2. Helium also produces spectral lines at specific wavelengths, but they have different properties than those of hydrogen. 3. Carbon. Carbon is a complex element with 6 electrons, and has a variety of energy levels and electron arrangements. 3. Carbon can absorb and emit light over a wide range of energies, resulting in a variety of spectral lines. 3. Carbon is used in a variety of chemical reactions and spectroscopic studies. Therefore, the type and composition of a chemical element are important factors that determine its interaction with light. This results in each chemical element having a unique spectrum and chemical properties, which are exploited in spectroscopy and chemical research. Specific examples. 1. The absorption of light by hydrogen atoms can be used to identify the presence of hydrogen in the sample. 2. The emission of light by helium atoms is used in neon signs. 3. The absorption of light by carbon atoms is used in infrared spectroscopy, which can be used to identify the presence of different types of carbon-containing molecules. Conclusion. The response of atoms to light is a complex phenomenon that is determined by the properties of the atom itself. This phenomenon is used in a variety of applications, including spectroscopy, chemistry, and physics.